In this video, we're going to take a look at section 3.4, linear programming. With linear programming, you are going to take a set of constraints and turn them into inequalities. You'll graph the inequalities and end up with a feasible region. Inside the feasible region are all of the possible solutions to your problem, whatever that might be. And then as it happens with linear programming, the vertices of your feasible region will determine the maximum or minimum values of the objective function that you're trying to solve. So we'll talk more about what this really means here in a minute. But let's go ahead and start with an example of linear programming where we're selling screen printed t-shirts and sweatshirts. So I've got a list of constraints here, and we're going to take these constraints one at a time and turn them into inequalities. So the first constraint is that we only have 20 hours to work. We can only work for 20 hours. Our second constraint is that we can only spend $600 on supplies. We can't go over $600 on supplies to make the t-shirts and sweatshirts. Also, we have to sell at least 50 t-shirts and sweatshirts. And then these are some other big ticket item constraints. With t-shirts, they take $4 to make. They earn us $6 in profit, and they take 10 minutes to make. Sweatshirts take 30 minutes to make. They cost $20 to make, and they'll earn us $20 in profit. All right, so let's talk constraints. So our two variables are going to be X and Y. I'm going to assign X to t-shirts, and I'm going to assign Y to sweatshirts. If you don't have all of this already written down, pause the video and write down the constraints, as well as the situation. We're selling screen printed t-shirts and sweatshirts. All right, once you get everything written down, including all of these black bullet points, let's start with our inequalities. So X is t-shirts, Y is sweatshirts. Now it says we only have 20 hours to work. So that means we have less than or equal to 20 hours to make t-shirts and sweatshirts. Now I happen to know something else about the time that it takes to do t-shirts and sweatshirts, and that is that t-shirts take 10 minutes and sweatshirts take 30 minutes. Now, I'm going to convert this 20 hours into minutes. 20 times 60 is going to be 1,200. So we're going to call this 1,200 minutes. That means we're also going to adjust our constraint. So that was a good start, but now let's think about this in terms of minutes. We have only 1,200 minutes to work, so less than or equal to 1,200 minutes. Remember that each t-shirt is 10 minutes and each sweatshirt is 30 minutes. So there's an inequality that describes our time constraint. Next up is we have no more than $600 to spend. So we need to stay under $600, under or equal to $600. When it comes to the money for supplies, remember that it takes $4 to make each t-shirt and $20 to make each sweatshirt. So I'm going to say 4X plus 20Y is less than or equal to $600 because this is going to be expenses. Maybe I should label this. First constraint was time. The second constraint is expense. What else do we know? We have to sell at least 50 items. So this total of 50, I need to go at least or over $50 or 50 items. So X plus Y needs to be greater than or equal to 50. All right, now I haven't done anything with the profit. I don't know how much profit that I want to make. I know that t-shirts are going to give me $6 in profit and sweatshirts $20 in profit. I'm going to go ahead and underline that, maybe in a different color. And then let's talk about the objective function. So this comes into play in the objective function. So the objective function models the quantity that we're trying to maximize or minimize. Well, in this case, we want to maximize the profit. We want to maximize the profit. So to maximize the profit, we're going to sell t-shirts and sweatshirts. And remember that each t-shirt will get us $6 in profit, and each sweatshirt will get us $20 in profit. So this is my objective function. We'll use that objective function here in a minute. Before we can use the objective function, we need to have a feasible region. So what I'm going to do is get myself another page and then look at these two pages side by side. Okay, so we're going to make a graph. Try and do this as carefully as possible. I'm really only going to work in the first quadrant because I wouldn't have a negative number of sweatshirts, a negative number of t-shirts, so that's unnecessary. Remember that X represents t-shirts. Go ahead and label your axes, and Y represents sweatshirts. Now I'm going to graph these equations one at a time. So the first equation to graph, and this is just kind of some sketch work right now, 10x plus 30y is less than or equal to 1200. I'm going to graph using the intercepts. 10x is equal to 1200, making x equal to 120. I'm going to mark that maybe right about here. Then I'm going to find my y-intercept. 30y is equal to 1200, and then 1200 divided by 30 would be y is equal to 400. No, that's just 40. Let's see, 40. I have one too many zeros. Let me erase that. Okay, whoa. Okay, so y is equal to 40. 30 times 40 would be 1200. Okay, go ahead and plot that point. 40, I'll put that right about here. Okay, point to point, connect the dots. Keep in mind that I need to stay underneath that. Now, the next equation I have to graph, and I think it's time to highlight. If you have different colored highlighters, this might be a good idea. So this constraint right here is this line right here. Okay, next constraint, expenses. That will be our next constraint to graph. I'm going to do that in a different color even. So down here, I'm going to do it in black. Okay, so 4x plus 20y is less than or equal to 600. Again with the intercepts. If 4x is equal to 600, x would be equal to 150. So x is 150, that puts me right about here. And then 20y is equal to 600. Y would be equal to 30, and that puts me right about here, we'll say. Connect those 2 points. They intersect right here. I'm not sure what that is, but we'll come up with that in a minute. And then, of course, I would be underneath again because I have to stay under $600 in expenses. Go ahead and highlight that next line, and you have it color-coded over here with blue and expenses. All right, then, last of our constraints to graph is x plus y is greater than or equal to 50. X plus y is greater than or equal to 50. So my x-intercept would be 50, my y-intercept would be 50. So here's 50 on the y-axis. Here is 50 on the axis, connect those dots. Now we want to stay over that, so that means we would be shading kind of in this direction. You can see that here's an intersection point and here's an intersection point. What we really need to kind of dig around though for is what is the feasible region? So I'm going to take a minute and kind of do some color coding. X plus y is greater than or equal to 50 is this line right here. And then where is the multi-shaded region? Well, my multi-shaded region is going to be everything in here. So really kind of shade that in. In this region are all of the possible combinations of t-shirts and sweatshirts that will satisfy all of my constraints. Let's review the constraints. The constraints are that I can only work for 1,200 minutes, I can spend no more than $600 on supplies, I have to sell at least 50 items, and the t-shirts cost $4 to make and 10 minutes to make. Sweatshirts cost $20 to make and take 30 minutes. All right, so Let's see, I think we've got everything covered. Like I said, this is our feasible region. The feasible region contains all of the possible solutions to this problem, so all of the combinations of sweatshirts and t-shirts. But let's go back and talk about this objective function. The objective function models the quantity that you're trying to maximize or minimize. Well, obviously, I want to maximize my profit. Remember, I get my profit by charging $6 for each t-shirt and $20 for each sweatshirt, and then, of course, actually selling that many. Well, your maximum or minimum, your quantity will always happen at the vertices. So what we need to do are look at all of the vertices of the feasible region. And the vertices of the feasible region are just the corner points. So I'm going to kind of pinpoint those in red. This is a vertex, and that vertex is over 50 up 0. That's a vertex, and it is over 120 up 0. This is a vertex right here, and that is a vertex right there. Now, I've already done some computations and come up with those two vertices. What I've done is elimination and substitution to solve for x or y. Actually, I did elimination. So I'm going to have you just take my word for it. So our other two vertices are 25, 25 and 75, 15. Again, I used a combination of elimination. I used a combination of these equations using elimination to find those intersection points. And I'll show you exactly how to do that tomorrow. All right, but for right now, what we're going to do with these vertices then is plug them into the objective function. So 6 times 50 plus 20 times 0. 20 times 0, that would be 6 times 50 is 300 plus 0, 300. Then 6 times 120 plus 20 times 0. Well, that would be 720. Then I'm going to go 6 times 75 plus 20 times 15. I'm going to use my calculator to calculate that. 6 times 75 plus 20 times 15 gives me 750. And then finally, 6 times 25 plus 20 times 25 equals, my calculator is working hard for me, 650. Okay. So remember, what we're trying to do is maximize our profit. Which of these vertices gives us the maximum profit? 75.15. So if I sell 75 t-shirts and 15 sweatshirts, I will maximize my profit while staying within my constraints. And that's it. Okay. So we're going to do a lot more examples in the next few days. We'll spend a few days on linear programming. It's one of my favorite things. In fact, we use linear programming on the farm each spring when we're trying to decide what combination of corn and soybeans to plant within our constraints. All right, good work.